Topic for today is indeterminate members. So as usual, we have an introduction. So recall, right? If the equilibrium equations are sufficient to calculate all the forces, including support reactions that act on a body, these forces are said to be statically determinate. Now, in contrast to that, we have statically indeterminate problems, okay, which is our topic for today. So here, if the number of unknown forces exceeds the number of independent equilibrium equations. So basically, in statically determinate problems, the number of unknown forces is equal to or less than the number of independent equilibrium equations. Now, in the case for statically indeterminate members, that's not the case. There's more unknowns than equations. So to remedy that, we have what we call compatibility equations. So these are mathematical expressions of the geometrical restrictions imposed on deformation. We're going to use geometry. So this means that free body diagrams are kind of important now. Okay. So compatibility equations provide the additional equation needed to solve the problem. Okay. Now you may have discussed this in your Mech 30 for method of members, right? For frames, your three equilibrium equations aren't enough to solve for the four unknowns for forces on the hinges of a member. It's kind of like this, okay? But now we have compatibility equations to give us more equations. So this is the procedure. First, draw the free body diagram and derive equations of equilibrium. Okay, so recall, the equations of equilibrium are summation of moment equals 0, summation of forces vertical equals 0, and summation of forces horizontal equals 0. Next step, draw a sketch that exaggerates the magnitude of deformations and derive compatibility equations. So this is why free body diagrams and sketches are important, because from those, we'll have our compatibility equation. Next, use Hooke's law to express deformations or strains. The compatibility equation in terms of forces or stresses depends on what is being asked in the problem. And then lastly, solve. Okay, so pretty straightforward. Let's try to have a few examples to better understand concepts. Okay, so for number 1, I'm going to solve this on my own. You just have to listen, and you can solve along if you want, but I'm not taking recitation yet. So number 1, a concrete post in the figure is reinforced actually with 4 symmetrically placed steel bars, each of cross-sectional area 900 millimeters squared. So this is your concrete post, as you can see, and these are your steel bars. So 4 steel bars at each corner. Compute the stress in each material when the 1000 kilonewton actual load is applied. The moduli of elasticity are 200 GPa for steel and 14 GPa for concrete. So basically, we're looking for stress in the concrete and in the steel. So let's begin by writing out our given. So we have this, number 1. Okay. So let's write first our given. First area of your steel bars. Okay, 900 millimeters squared. So let's write ASP for area of steel bars. 900 millimeters squared. What else is given? Your 1000 kilonewton force, and then moduli of elasticity, 200 for steel, 14 for concrete. Okay, so G for the steel is 200 GPa. And then G for concrete So let's call that G sub C for concrete, 14 GPa. Okay. So basically, again, we have this applied force being resisted by the concrete and your 4 steel bars. So let's try to draw a sketch of what's happening. Okay. Try doing 3D. Okay. So you have your concrete, and then we have steel bars here. Okay. Okay. Now, this cross section is being or is experiencing. Okay. Okay. It's experiencing this 1,000 kilonewton load. Now, the parts that are resisting this load are your concrete. Let's draw concrete. So first this, okay, the actual concrete. So let's call that PC. And then your individual bars. Okay. So let's choose this. Yeah. Okay. So these are your reaction of the steel bars. So PST for steel. Okay, so that's what's happening. Now to get a clearer view, we can draw also a 2D version of this, which looks something like this. Okay. So you have your plate, your bar, and since this is just front view, you can only see 2 at a time, right? Then again, we have this applied force, 1,000 kilonewton. And since again this front view, this is now actually this area considers 2 bars, 1, 2, 1, 2. Okay, so this now becomes 2 PST. Same here, 2 PST. Then don't forget concrete also resisting the force. So we have PC. Okay, from this drawing, you can create our equilibrium equations. So specifically, summation of forces equals 0. They're all in one direction, so you can either write forces y or just forces equals 0. Okay. So sign convention applies, upward or positive. So 2 PST plus 2 PST, that's 4 PST plus PC minus 1,000 kilonewton. Now, remember our standard units are MPa, and that's Newton per millimeter squared. So as much as possible, if convenient, convert everything to Newton millimeter. Okay? So convert to Newton. So that is times 1,000. So you can just write times 10 raised to 3 so that it's converted to Newton. Okay, and then equate that to 0. So you have your initial equation from an equilibrium equation. Now take note, we're looking for stress. Okay, so that means I should convert this force into stress. And remember, stress stress equals force over area. Therefore, force is just stress times area. So I'm gonna rewrite all of this into force equals stress times area. So stress ST, area ST, then plus PC. So that's stress C plus area C. Then I'll just transpose this force to the other side. Can you guys hear the storm over here? Or is it being filtered out? Hmm? Can you hear the rain over at my area? Or di naman? Okay, that's great. It's very loud here. So that's good. Continuing. Now that you have this equation, you can sub in the values that we know. This is what we're looking for, stress ST and stress C. Cross-sectional area of steel is given. It's 900 millimeters squared. Already standard units, no need to convert. So let's write that as 4. I'm going to move here. 4 stress ST times 900. Okay? Then plus stress for concrete. Area of concrete. How are you going to do that? So you can see here, that's the cross-sectional area of your concrete. So it's basically a square. Okay? Because it's 300 by 300. So area of a square is side squared. So 300 squared. However, we have these steel bars. So you need to subtract. Because basically these are holes for the concrete. So minus, there's 4 of them. So 4 times 900. Okay? Then equals 1000 times 10 raised to 3 or 1 times 10 raised to 6. Okay, this is just simplifying the number. You can just have this, or if you want, you can simplify this further so that the equation is easier to see. So 900 times 4, that's 3,600 sigma ST plus 300 squared minus 4 times 900. That is 86,400 sigma C equals 1 times 10 raised to 6. And basically, we now have an equation number 1. So we have okay. So we have 2 unknowns, just 1 equation. So this is an example of statically indeterminate. Okay, because there's no other equilibrium equation we can use. So now the next step is to try to create compatibility equations by exaggerating the deformation of your objects or your body. Let's do that. So we have this, right? Yeah. Okay. So let's say that's a portion of your body. Okay. And then because of this force, right? That body will contract, right? Because the force is compressive. So it's gonna deform this way. Okay? Right? So this is now the final position. Let me just get a new color. Okay? Great. Yan. Okay, you can see. So what happened there is, this is the original position of your body. Because of this compressive force, it ended up here. So to compute, right? Okay, this is a bearing plate, so you don't need to include that. This is how much your concrete retracted or compressed, right? That is the deformation of your concrete. And in at the same way, this is also how much your steel compressed, right? So that's your deformation of steel. So based on this drawing, you can see that the deformation of concrete and steel are equal, okay? Because they move at the same time. So from that, our compatibility equation now is, yeah, deformation of steel equals deformation of concrete. Next step is to create equation for deformation. We have two equations, right? Sigma L over E and PL over AE. If I remember, we're looking for stress. So we're going to use sigma L over E. So sigma L over E for steel. Okay. So again, this just means these variables are for steel. Then equals sigma L over E for concrete. And then sub in your values. Now look at length. L is original length, okay? Original length of steel and concrete is this. And they're equal. So meaning, I can cancel that out. Okay? So now we have stress in steel. So just a bit of a warning, if I suddenly got cut off, there could be a blackout in my area because the storm is so strong here. Okay, so just a heads up, if I suddenly disappeared, brown out over here or blackout over here. Okay. So anyway, continuing. Stress of steel over E. So E of steel we already know, or you should know, is 200 GPa. Okay. And then to convert GPa to MPa, that's just times 1000. Okay. So this becomes 200 times 10 raised to 3. Do the same thing for the other side. So equal sigma C over the modulus of elasticity of concrete is 14. Again, convert to MPa. So that's times 10 raised to 3. Move things around. You'll get 14 times 10 raised to 3 sigma ST, right? Minus, okay, I'm gonna transpose that to the left. So minus 200 times 10 raised to 3 sigma C equals 0. And this is your equation number 2. Two equations, two unknowns. You can either use your calculator or solve manually for sigma ST and sigma C. So therefore, again, you can try at home, use your calculator, or manually solve. You should get these answers. Sigma ST is 103.65, and the unit is MPa, since we converted everything to Newton and millimeter. So MPa, and then sigma C is 7.26 MPa. And these are the stresses being experienced by your body or structure. Okay, that's number 1. Any questions for number 1? Please answer in the chat. Okay. Next, let's move on to number 2. We don't have questions. Number 2, kind of similar to number 1. Now I'm going to take recitation, okay? So prepare your calculators. A steel bar 50 millimeters in diameter and 2 meters long is surrounded by a shell of a cast iron 5 millimeters thick. Compute the load that will compress the combined bar to a total of 0.8 millimeters in the length of 2 meters. For steel, E is 200 GPa. For cast iron, E is 100 GPa. So to analyze, basically we have steel bar surrounded by iron. Now the question is, what force do we need so that the entire thing will compress by 0.8 millimeters? So it's the opposite of the previous question. In the previous question, given force, we're looking for stress. Now here, given deformation, looking for force. Okay? So let's begin by again writing out the given. So steel bar 50 millimeters in diameter. Let's call that DST. Next, 2 meters long. That's the longitudinal length of your structure, so we can call that L. What else? Cast iron 5 millimeters thick. So let's just write thickness of iron. So that's Fe for iron. It's already written here, but we can rewrite. And then this is our deformation, 0.8 millimeters. So total deformation, 0.8 millimeters. Okay. Again, they're both 2 meters. And then lastly, 200 and 100. Okay. And then G of iron, again, let's call that Fe, 100 GPa. Okay, so that's all you're given. Next step, create free body diagram of what's happening to use your equilibrium equations. So once again, what's happening here is okay, okay, okay. So basically, this is what's happening, right? Again, you have an applied force, which is what we're looking for. We're looking for P. And then this force P is being resisted by your structure, which is composed of 2 materials. First is your steel. So there's a reaction of steel here. Let's call that PST. And there's also a reaction from your iron. Okay, so there's another reaction here. So PFE. So that's your free body diagram. Now create your equilibrium equation. So summation of forces equals 0. So let's see. ST and FE are both upwards, so positive. PST plus PFE. P is downward, so negative P equals 0. Okay? You can rewrite this as P equals PSP plus PFE. Once again, that's your equation number. Next, let's find out your compatibility equations by drawing out what's happening when this compresses. So let's do a front view. Okay. So again, let's choose column. Steel. That's your steel. And these are your iron. Okay. So that's the original. Actually, let's do it this way. Yeah. So that's the original, right? And then again, because of force, it moves this way. It compresses. Okay. And then okay. And how much are they compressed? By 0.8 millimeters. So this is how much it compresses. 0.8 millimeters. And that's also and this is also the amount that both your iron and your steel deforms, because again they move together. So steel equals deformation of your iron. Okay, and then from this you can create your equation. So deformation of steel equals deformation of iron equals 0.8 millimeters. And then sub in your equation. We're looking for force. So the equation for deformation that we'll use is what? Can anybody give me what equation for deformation should I use? There's only basically two. I already used the other one. What should I use here? Equation for strain. Very good, Sierra. PL over A. So PL over AE of steel equals PL over AE of iron, and it's equal to 0.8. Next step, sub in your values. Once again, original length of iron and steel are the same as 2 meters. So we can just cancel that out. Next, P. This P is the force exerted by your steel. So that's PSP. Cross-sectional area, is it given? Nope. Compute for it. So the total diameter of everything is 60, right? But for steel, it's only 50. So that's just pi over 4d squared, since it's a circle. So PSP over yep. You can't cancel this because you equated it to 0.8. There's no L here, so I can't cancel everything. Okay, so keep it. Okay, again, can't cancel. PST. Total length of your steel is 2 meters. Remember, convert everything to Newton and millimeter. So this is 2,000 millimeters over area. This is steel. It's a circular cross-sectional area, so that's pi over 4. Diameter was 50 millimeters squared. Then E is 200 GPa. Convert to MPa, that's just times 1,000 again. Okay? Or times 10 raised to 3. Equate that for iron, so PFE. Its length is still 2 meters or 2,000 millimeters. Now, what is the cross-sectional area of your iron? It's this. It's only this, right? Or this. So that's just a ring, the area of a ring. And the area of a ring is just 5/4 diameter outer squared over inner diameter squared. So 5/4 outer diameter is 60 minus 50 squared. Okay? So 5/4, 60 squared minus 50 squared, and its E is 100. Convert again to MPa, that's times 10 raised to 3. Then equate that to 0.8. So basically, we have two equations. PST equals 0.8, PFE equals 0.8. And from both, we can solve for PST. Can anybody please solve what's PST? Just equate it to 0.8, this equation. Then please solve PST. Correct, Aaron and Audrey. Enrique and Cos. Okay, it's, let me say, 157.08 kilonewton or 157,079.63 Newton, or if your calculator did this, your PST is actually, the easier way to write is 50,000 pi. Okay, just so I don't have to store anything. This is also equal to 50,000 pi. And then in the same way, please solve what's PFE. Okay, good. Michaela and Audrey. So Santos and Manuel. 2 points. So 11,000 pi. Okay, now that you have these two, you can sub it in equation 1. So P equals PST is 50,000 pi plus 11,000. Please solve what's the final answer. Correct, Micaela and J. Santos and Lomibao. It's 191,637.15 newtons. Okay, or 191.64 kilonewton. Okay, there. So that's number 2. Any questions for number 2? Please answer in the chat. Okay, good. Let's move on to number 3. since you don't have questions. So number 3. So number 3 is a bit different now. The rigid platform in the figure has negligible mass and rests on 2 steel bars, each 250 millimeters long. The center bar is aluminum and 249.90 millimeters long. Compute the stress in the aluminum bar after the center load for 100 kilonewton has been applied. For each steel bar, the area is 1,200 millimeters squared and E is 200 GPa. For the aluminum bar, the area is 2,400 millimeters squared and E is 70 GPa. So basically, we have this force, right? Only steel is initially supporting it. Now the question is this force, which is 400 kilonewton, enough for this bar to close this gap? And then, because the gap is closed, your bar is now resting on the aluminum bar. Now we want to know what stress is it experiencing if that is the case. Okay? So again, to solve for this, we're going to assume that yes, 400 kilonewtons is enough for this bar to touch the aluminum bar. Okay? Then, first step, write out the given. So, steel bar, 250 millimeters long. That's the first one. Okay, so length of steel bars. So, LSP. Next, L aluminum is 249.90. Okay. Next, P is 400 kilonewton. Okay. What else? Area is 1,200 and then 200 GPa and then 2,470 GPa. So area steel 1,200 and then E should be E. Just got mixed up in the variables. Okay, so fix that. Going back. E is for steel, again, just 200 GPa. And then area of aluminum, 2,400. And then modulus elasticity is 70 GPa. Okay, there, that's all of the given. Let's solve, draw free body diagram. And once again, we assume, what do we call this? Platform reaches aluminum bar. Okay? So since that's the case, the free body diagram will be like this. Right? So this is your platform. There's reactions here at this point. Right? PST. PST. And then at the center, your aluminum also gets to react since your platform reaches it. So PAL. And then we have an external force here, 400 kilonewton. Okay, from this, it's easy to create your equilibrium equation. So summation of forces equals 0. So PST, so that's 2 PST plus PAL equal minus, since downward, 400 kilonewton. Again, convert to Newton times 10 raised to 3 equals 0. Now remember, what are we looking for? Stress in the aluminum bar. So we need to convert that equation into stress. Again, stress is force over area, so force is stress times area. So twice stress ST, area ST, plus sigma AL, area AL, and you can just transpose 400 times 10 raised to 3. Next, you can sub in the values that you know. So twice sigma ST, area of steel is given already in millimeters, so no need to convert, 1,200. And then plus sigma AL, this is 2,400 400 times 10 raised to 3. Okay, so you can simplify this if you want, or you can just call it as equation number 1. Okay, up to you. Let's try just using it as is. All right, now you're done with the equilibrium equation. Next step is to find out the compatibility equations. So again, let's draw the original position of everything. I'm gonna exaggerate. Okay. Then this is not touching. Okay. Okay. And then so as you can see, basically it's gonna move down, right? Okay. Only the bar goes down. Okay. So what happens? This entire thing goes down because of that force. So let's say its final position is here, right? And so you can see clearer. And let's use red. Hope you can see. But basically, this platform is now this platform in its final position, right? And this gap, if this is 250, this 249, then this gap is 0.1 millimeters, right? So this is 0.1 millimeter. And then, okay, this is how much your steel bar contracts. Okay, so sigma ST. And then this tiny thing, if ever, is how much your aluminum bar contracts. Okay, then can you see? That's the final position of your platform. Initial position of platform goes down here, and then everything compresses. Okay. Okay. So from this, you can see the equilibrium equation. As you can see, sigma ST is just equal to this, which is 0.1 plus sigma AM. Okay. So again, that's why free body diagram is important, because from your drawing is where you'll create or get your equation. Okay. So once again, deformation of steel is equal to 0.1 plus deformation of aluminum. So deformation of aluminum plus 0.1 millimeter. Okay, now let's create our equations. Once again, we're concerned with stress. So we're going to use the equation sigma L over E for steel, sigma L over E for aluminum plus 0.1. Okay, now sub in stress of steel. Next, length of steel bar. Again, it's 250. Already in millimeters. Next, this is 200, right? By now, you should memorize modulus of elasticity of steel is 200 GPa. Convert to MPa times 1000. Equals stress of steel. So that's AL. Length of steel is 249.90. Over, what was that? 70. So 70 times 10 raised to 3. And then plus 0.1 millimeter. Okay. Now from this, again, you can simplify. Or if you're used to solving your calculator, you can already figure it out. You can use this directly as your equation number 2. Okay? Two equations, two unknowns. We can solve for what's being asked. And the only thing being asked is stress in aluminum bar. So you only need sigma AL. Please solve what's sigma AL. Correct, it's 22.48. Correct, Beatrice and Trinity. So Pascual lang. Again, two equations, two unknowns. You can rewrite this in a more simplified manner if that helps you out. But to make things quicker, you can just use this. So the answer was 22.48. All our units in Newton millimeter, therefore stress is MPa. There. So that's number 3. Any questions for number 3? Please answer in the chat. What about the others? Please answer as well. Any questions? Okay, great. Since you don't have any questions, let's move on to number 4. There. Number 4. A homogeneous bar with a cross-sectional area of 500 millimeters squared is attached to rigid supports. It carries the actual loads P1 equals 25 kilonewton and P2 50 kilonewton applied as shown in the figure. Determine the stress in segment BC. So it's pretty straightforward. Homogeneous bar meaning it's the same material all throughout. So meaning its modulus of elasticity is the same. And then the only thing we're looking for is stress in BC. So here. Okay, let's figure that out. So write out our given. The only given are the forces. So let's have that 25 and 50. Okay. And then area, we also have that. Was it 500 millimeters squared? Okay. So now, next, complete your free body diagram. This will create reactions at support. Okay. So if you try to simplify it, we have this. And then we have this. 25 kilonewton. We also have this 50 kilonewton. And aside from that, you're going to have reactions at your supports, which are at the end. So here, okay, you're going to guess the direction. So since my forces are to the right, I'm going to make an intelligent guess. Perhaps the reaction here is to the left to counter these two forces. Okay, and let's call that RA for reaction at A. And then same thing here, since you have two forces here to the right, counter that, maybe there's a force here to the left. Again, this is just guessing direction. Let's call that RD, reaction at B. Okay, now you have your free body diagram. You can create an equation. So summation of forces equals 0, negative RA plus 25 kilonewton convert to newton, 25 times 10 raised to 3 plus 50 times 10 raised to 3 minus RD equals 0. Simplify. Okay, transpose RA and RD to the right. Becomes positive. So RA plus RD, and then 25 plus 50 is 75,000. Okay, so now you have your first equilibrium equation. Next, let's figure out what happens. But before that, the question was specific. We're looking for stress along BC. And recalling our topic for stress, whenever looking for stress along a certain segment, we need to figure out first its internal force. Okay, so we need to find out force within member BC or segment BC. And how do we do that? Okay, to do that, remember, you cut isolate. So let's say this is your BC, right? Let's cut here, right? So A, B. Then there's force here. So I'm gonna cut here, then I isolated the left side. Okay. There's also RA here. Then you're gonna assume the direction of your force. Is it compression or tension? So this is just a guess. Maybe it's compression. I'm just guessing. Stress BC is in compression. Oh no, tension. Makes more sense. Okay. Why? Because this portion is pulling, but this is greater. So the amount BC stretches is greater than it compresses. So I'm just gonna guess the internal force here is in tension. So PBC. Okay. Then from this, you can create another equation. Summation of forces equals 0. Negative RA plus 25,000 plus PBC equals 0. And this is our goal. The goal is to get PBC since you already know the area. So that stress is force over area. That is how we'll solve for stress in BC. Okay? So PBC is just RA minus 25,000. Okay? And let's call that equation number 2. Great, so now you have your set of equations. Next step now is to actually get your compatibility equation. So how? So let's do this, right? Now in actual, your bar is not able to stretch, right? Because it's between fixed supports. The presence of these two things prevents it from compressing or stretching. So meaning total deformation of all your segments is 0. So knowing that, okay, you can either do summation of stress AB plus stress BC plus stress CB equals 0. Now the problem there is you have to figure out which segment is in tension and which segment is in compression. Okay, so let's begin with our analysis. So this is the initial starting point of B. And then this is the initial starting point of C. Okay. So when it moves, let's find out the final position. Okay, so I'm just gonna choose some colors. Orange, blue. Okay. Now what happens here? Let me just get a copy. Mm, Okay. So because of the presence of this tension force, right, this bar will elongate. So the final position of B will be somewhere here. Okay. Then, since this moves, the final position of C also moves. Okay. So this is now the final position of C because of the 25 kilonewton force. Now C will move again because of this 50 kilonewton force. So it's going to move again by some amount here. Okay. So now, this is your final segment B, right? And then B. And if you've noticed, the total deformation of B is this much, right? And this portion is a deformation due to this 25 kilonewton force, right? So that's basically deformation of BC, okay? Or deformation, how much this moved. Okay? You can also say that is how much AB elongated. Okay? So again, this 25 kilonewton force causes B to move here, so bar AB elongates. Okay? How much this elongated is equal to how much this elongated as well, right? So now we've established this is elongation of AB. And then this is elongation of BC because of the 50 kilonewton force, okay? And then this entire thing is how much segment CD compressed. So let's put that into variables, okay? So once again, this is how much section AB expanded, okay, which created this side to move as well. So this is your segment AB, okay, or elongation of AB. Next, this portion of BC also moves because of the 50 kilonewton force. So this amount, okay, so after BC moved here, it's gonna move again because of 50. So now this is the stress, elongation of AB, and this is the elongation of BC. Okay, and then this entire thing is how much segment CD contracted. Okay, so from this, you can create your equilibrium equation. Sigma AB plus sigma BC is equal to how much it contracted. Or if you don't want to write it that way, okay, elongation plus elongation, and then contraction is negative, so negative CD equals 0. Okay, so you can do this or equate that to CD. Okay, it's the same. Next step, write out your equation. Once again, the goal is to get PBC. So I'm going to write my equations in forces. Okay, so PL over AE of force AB plus PL over AB, AE of segment BC equals PL over AE of segment CB. Next, once again, this is a homogeneous form. All of their area and modulus of elasticity are equal. Therefore, you can just cancel all of it out. Okay. So next PAB, right? And length. Again, L is original length. So 0.60 meters or 600 millimeters. Okay, 600 plus PBC. Again, this is what we need. Then its original length is 1.2 meters, 1,200 millimeters. Then equals PCD, which is 90 or 900 millimeters. Now the problem here is there's a lot of unknowns, right? But we go back here, right? We got this side and this side. Okay, let's do that. This is RA. Again, this is cutting here. Therefore, this is PAB. Do the same thing on this end. There's RD over here. Then cutting, cut isolate up here. Okay. You will get your internal force in segment CD. So PCD. Then from this equilibrium equation, summation of forces equals 0, you'll see that PAB is just actually RA. Same thing here, summation of forces equals 0. PCD is just equal to RD. Okay, so going back here, PAB is RA. So 600 RA plus 1,200 PBC. And what is PBC? PBC is here. RA minus 25 times 10 raised to 3. Equals what's PCD RD. Then 900 RD. Now you might be wondering why, since I'm looking for PBC, why did I convert it to RA? Because if I didn't, we'd have 3 unknowns still. But now we just have 2 RA and RD. And now we can call this equation 2. Okay? But look here. Equation 1, unknown are RA and RD. Equation 2, the only unknown is also RA and RD. So 2 equations, 2 unknowns. You can solve for what's missing. Now specifically, again, the goal is to get PBC. To get PBC, I only need RA. So please solve what's RA using the 2 equations. Correct Trinity and Elika, Lambda and Lambda. 36.11. Oops, that's not equation 2. It's equation 3. So using 1 and 3, you can solve for RA. And again, RA is 36.11 kilonewton, but our units are in Newton. So that's 36,111.11 Newton. Okay? Again, 36.11 kilonewton. Now that you have RA, sub in 2. So sub that here, then please solve what's PAB. Wait, PBC rather. Correct John and Elika. So, Mitan and Daub. It's 11.11 kilonewton, or again, our answers were in Newton, so 11,111.11 Newton. Okay, so now I have a force. So to get stress in member BC, that's just P BC over A BC. PBC is this, 11,000. Area is 500. So please solve what is stress BC. Correct. Correct, Ronel and Vanessa. Wano is the okay. So 22.22. Again, everything was in Newton and millimeter, so stress is in MPa. Okay. There, that's our answer. Also, take note, okay, our answer for PBC is positive. Therefore, our assumption that PAB is tension is correct. So tensile force, here. Our assumption that PBC is in tension is correct. So tensile force creates tensile stress. So tensile. Don't forget type of stress it is. Compression or tension. Okay. All right, so that's number 4. Any questions for number 4? Please answer in the chat. Okay, great. Now, what if your assumption was incorrect? You assume this was in compression. What will happen? Let me show you. Okay, so that's what will happen. The first part is the same, right? You still got your equation number 1. Now here, okay, instead of assuming tension, you assume compression. So your new equation will become this. PBC is now negative RA plus 25 times 10 raised to 3. Now, since this is in compression, right, only segment AB expands. Okay, so this is the final length of AB. Now, BC, again, you assume to be in compression, so it's going to compress, right? Same thing with CD. Therefore, if you're going to create your equation, only only deformation or delta AB is positive. So you'll get delta AB minus delta BC and delta minus delta CD because they're both in compression equals 0. Or again, you can rewrite as delta AB or deformation AB equals deformation BC plus CD. Okay, and then you're going to go through again your equations, but now the answer that you'll get you'll still get 36.11 kilonewton for RA. But when you sub this in equation 2, you'll get negative for PBC. Okay? So since it's negative, incorrect assumption here, it should be in tension. Then you're going to correct that in your final answer, tension. Okay? That's what happens when you have an incorrect assumption for direction. Okay. So, it's almost time. I'm going to end the lecture there. Okay? So before I dismiss you, I have a few announcements. On Thursday, continuation of problems. Okay, there's only 2 left. Okay? And then we're going to start a new topic, thermal stress. Okay, that's on Thursday. On Saturday, your quiz number 2. The coverage will just be up to indeterminate members. Okay, so thermal stress is not included yet. Next, for those who got an IP grade, okay, I'm gonna upload an exam later or tomorrow, hopefully within the week. I'm gonna show you where. So I haven't uploaded it yet, but here at the bottom, you'll see IP activities tab. Click that IP activities. You're gonna go to module 1, and then there's gonna be an IP exam. Just answer that. Okay? Again, this is only for students with an IP. Answer that. It's unlimited attempts. You're gonna answer as much as you want. And then there's gonna be a new grade column for you guys. For those who got IP, its name is, I believe, M1 or MG1, then parenthesis for IP students. Okay. Just look out for the grade with the name at the end for IP students. Okay. So as when you answer the exam, whatever score you get, your module grade for IP students will update immediately. So that means you have to answer the IP exam until you get a score high enough so that your M1 grade for IP students is 70 or higher. Okay? So again, only attempts real time, your grade updates real time. Okay? You have until the end of the term to answer that. Now, for those who didn't get an IP, you can just ignore all of that. I and IP the same. Okay, you'll answer IP exam. Okay? And I and IP are the same. Or rather in what you're gonna do. Okay, so for those who didn't get an IP, just ignore that. Okay, if you pass module 1, just ignore that tab, like the exam tab, and because you still see the grade as well. Just ignore that. Okay. Now your module grade 1 is not done. I believe I haven't added your plus points and deductions, so I'll do that later as well. So tomorrow is when you'll see your final module 1 grade, so that you'll know if you should take the IP exam or not. Again, you can take the IP exam on your own time, whenever you want, as much as you want. Okay? Any concerns, questions so far, clarifications before I dismiss you? Okay. All right. Again, Thursday, continuation of lecture, quiz 1, quiz 2 on Saturday. Now, we also have an activity if you've noticed. Week 5, you have your midterm assessment. Okay, so this is what you'll do for your midterm assessment. You can either use Word or PDF file, it's fine, doesn't matter. So you're just gonna answer the following, similar to your course expectation. Number 1, what have you learned so far in this class? So basically, you'll just write down what you understood the most, your favorite topics, meaning the topics that you could teach someone else if needed, topics that you could have mastered. You can also write topics that were a bit harder for you to understand. Okay, so don't just write the topics in your syllabus. Okay, just include what you really understood. The number two, what do you want to improve about the class? You can write there that maybe I'm talking too fast, the pacing is too fast, quizzes are too hard, it's a bit unorganized. Any critique that you have, write it there. Number three, what would you like or want to keep about the class? Now you may like the pacing, you like how fast it is, you like how things are presented, you like the bonus points, quiz show, whatever. Just write whatever you want to keep for this class, for the remaining term, and for the next term as well for the incoming students. And then number four, what do you think about your overall performance in this class so far? So are you satisfied with your grade? Are you happy with the scores that you've been getting, or are you disappointed in how you did? Do you think you can do better? Just explain that there. And then lastly, number five, suggestions. Anything you want to say? Is there an activity that you want to do? Is there a game you want to play during class? Anything else you want to say? Write it there in number five. Okay? That's midterm assessment. Again, it should be at week 5. However, I wasn't able to tell you guys. So it's found in week 5, not 6 or 7. Just answer that. And deadline is July 10, 11:59 p.m., the same day for your quiz number 2. Okay? I think that's it. No more questions, clarifications. All right. So since you don't have any more questions, you may go. Goodbye, class.